So the first trend we're going to look at is atomic radius. Atomic radius is just the distance between the nucleus and the outer edge of the electron cloud, or your valence electron. So we're talking about the distance between the center to that outside electron. Okay, center to the outside electron. So already I hope you see in this picture that lithium has a smaller atomic radius than something like potassium. These are your alkali metals, meaning they're in group 1. So as we move down our column or our group, we're adding an additional energy level, period, and that is going to give us that bigger radius. Now, it is a little more than just different layers. So let's look at what our two main factors are that we're going to be talking about. So the first one is that is the idea of the layers, and I'll just zoom in on this little sentence right here. And so what it says is that full energy levels provide some shielding between the nucleus and the valence electron. So it's not just the idea that, we're putting on layers and layers, just like as things are cooling down, we're putting on layers and layers of coats. It's not like that where as we put on a new layer, we get a little bit bigger, a little bit bigger, a little bit bigger. It's not just that. What it also is, and I'm just going to zoom in on that picture again, is that you now have things in between, right? So here we have the nucleus, and then we're going to be communicating with that outside electron. When we mean communication, means that they're attracted to each other. So we've got valence electron is attracted to the protons in the nucleus. Here we have those valence electrons are still attracted, but there's stuff in between, right? There's stuff in the way. And here we have more stuff in the way. Just like our coats are going to be blocking out the cold, so do these layers. They start to block out that attraction. So when you are blocking some of that attraction, you're ultimately holding those outer electrons just a tad bit looser than something where the electrons are almost in direct contact with those protons, okay? Now, they aren't in direct contact. There's always space, but you get what I mean. So now let's look at what the other reason that we have this trend, the atomic radius, and it's going to be something called effective nuclear charge. So let me just adjust our picture here, and then we can look at this. All right, so effective nuclear charge, okay? Effective nuclear charge kind of sounds a little scary. It's a little, and we have this weird Zeph looking thing, but what it is talking about your protons, all right? So you have protons. We know that. As you look across the periodic table, we have atomic numbers that go up in size by 1, right? Those atomic numbers are equal to your protons, all right? And that's going to play such a huge role because if I have more protons in the center, right? If I have a bunch more protons in the center, and as I move across the period, I have even more protons in the center and even more protons in the center, then we have this idea that those protons are like a bigger magnet. They're like a bigger magnet. And just like we know with magnets from our cartoons or anything, those magnets are going to be attracting the opposite charge, right? So that attracts metals to this magnet. And so if we have a small magnet versus a big magnet, you can kind of imagine that something like chlorine over here, who has more protons than someone like sodium, is going to have this huge magnet and it's going to bring that electron in just a little bit tighter. So what we're going to see is that's going to shrink things going across. So again, in a nutshell, we have two ideas that all of these trends are going to be based on. And they are that we have shielding effect or layers. Okay, so we have layers. And we have protons in the center. We have an increasing number of protons going across this periodic table until we add another layer. And then we once again add more protons going across and we add another layer. Okay, so they kind of work hand in hand to give us all the trends that we're going to see. So when we look at the periodic table as a big picture here, okay, you can already see this trend, and you saw this in your web quest that you guys did yesterday, that as you move down a group, we noticed that the size was getting bigger. So these pictures right here are representing the atomic radius. As we move down a group, it gets bigger. If we look the other direction, and remember, you want to ignore, for now, we're going to not really pay too much attention to our transition metals. They kind of have their own set of rules at times, and we'll get more into that in the next chapter. But looking at our main group elements, the trend that we see as you move across the periodic table is that group 1 is a whole lot bigger than group 18 or group 17, okay? So as we move across, we're going to decrease in size. Okay, so to look at the pictures that we just saw in the last slide, okay, this is representing, this is representing your group 1. So again, group 1 right here. So this is lithium, sodium, potassium. So remember, these are getting bigger. So as we move down the group, they get bigger because of layers. And more importantly, those layers are going to cause a shielding effect, meaning it's going to block out that communication between that nucleus, the positive nucleus, and a negative electron out here. When we move across, we're going to be decreasing in size. And just a reminder from what we just saw on the last page, again, that as we move across the period, the idea is that we are going to have more protons. So as we see on our periodic table, the atomic number is what is getting bigger as we move across, right? So the example that we're looking at right there is sodium, and we go to aluminum, and we go to chlorine. We have an 11 versus a 13 versus a 17. So remember that the atomic number is representing your protons. If I increase my number of protons, which we just saw was 11, 13, and 17, then you can kind of visualize the idea of a smaller magnet, a medium magnet, and a super huge magnet, and they're just pulling in. All right, so this is a stronger magnet, meaning it's pulling in a whole lot more than something like the 11 magnet. All right, so as we move across, we are increasing our number of protons, the effective nuclear charge. And that pull from those protons is going to pull those electrons in very, very tightly. So we see that radius increases as we go down a group, and it decreases as we move across a period. So in conclusion, we have two different corners. We have the bigger corner, where you can see kind of this little cartoon picture of an atom, and we have a little cartoon picture of an atom right here. Okay, and so this will be your small corner, okay? Meaning, as we move this direction, we are decreasing or getting smaller. And as we move down the table, we are increasing or getting bigger, okay? So remember those two general corners, all right? And remember that the reason why is because we have more layers with that higher shielding effect, okay? So as we move to each period, we add another layer. And as we move across, remember that you have a higher number of protons, so it's effective nuclear charge. So think of the bigger magnet from the center. It's not really a magnet, but think magnet. All right, so let's try a couple examples to see if we can figure this out. So for example, on this first one, we have lithium and we have sodium. So we're going to go ahead and highlight. Lithium is right here, sodium is right beneath it. So you have to think to yourself, which argument are we trying to figure out? Which way of thinking should we be using? So we are looking at something that is down a column. When you're looking down a column or down a group, you need to be thinking layers. So now that we're thinking about layers, you look at the numbers that are off on the left. This one has a 1, this one has a 2, this one has a 3. So what you think about is we have 2 layers versus 3 layers. Oops. Right? So now that we know that we're looking at 2 versus 3 layers, hopefully you can already figure it out in your brain that the 3 is going to be the bigger atom. The other way to be thinking of that is that you can say, okay, which one is closer to this corner down here where we've said this is where the biggest atom is? So out of lithium or sodium, sodium is closer to being on the bigger corner. Let's look at the next one. We have nitrogen and oxygen. So looking at nitrogen and oxygen, so our next example is going to be talking about nitrogen or oxygen. So let's find nitrogen and oxygen on our periodic table. So we have, here's nitrogen, here is oxygen, okay? So we want to, once again, we're figuring out which one is bigger. So think about where they're located. These two, nitrogen and oxygen, are talking about the trend that is going across the periodic table, okay? So, since they're going across, then we are thinking, since they're going across, we're thinking about number of protons, okay? Think about the magnet idea. So a bigger magnet versus a smaller magnet, right? And remember, if we have a bigger magnet, then that's telling me that it's going to hold it in very tight. So the more protons, the more it's holding in tighter. So think of a magnet. Again, it goes big, medium, small as you move across. And once again, your layers, we already talked about this, was small, medium, big, right? So knowing that, nitrogen versus oxygen, we know that oxygen has an atomic number of 8, and nitrogen has an atomic number of 7. So therefore, the 7 is not as strong of a magnet, so it's being held a little bit looser. So nitrogen is going to be the bigger one. An easier way to kind of do this on your own is going to be also looking at the idea that this is our big corner, this is our smaller corner. So out of these two, who is closer to being near the big corner? That would be nitrogen. Nitrogen is more to the left, so it's more towards this corner right here. Okay? If you need to, take out a ruler, measure them. That can help too, but this is your big corner. Okay? All right, let's look at one more example. Atomic number 12 or atomic number 18. So looking at atomic number 12 or 18. So 12 is right here. 18 is over here. So if we notice, both of these are in row 3. So we know that we're talking about the across one again, just like that. Okay? So as we move across, we get smaller. So 12 versus 18. 18 is definitely going to have the bigger pull in, which means it'll be the smallest. So we're looking for the one that is further to the left or the one who has a smaller magnet, atomic number 12. Now the last one we're going to deal with is atomic number 12 or atomic number 56. So here is my 12 again. 56 is going to be right here, barium. So looking at 12 versus 56, okay, let me highlight these in purple actually. There we go. So 12 versus 56 means that this is an up-down idea. So remember, we're looking at the layers, okay? So we're looking at layers for this one. So 12 is up here in layer 3. 56 is down here in layer 6. So we have 3 versus 6 layers this time. So the one with 6 is going to be greater. Atomic 56 is a bigger atom. Once again, just to re-emphasize the corner idea, the other way to do this, if you don't want to think about layers or magnets, is look at the corner. Here's our bigger corner. So out of this one up here and this one right here, who is closer to the big corner? That would be barium. One last thing that I would like to leave you guys with, because we'll continue this analogy tomorrow with your ionization energy and electronegativity, is just that with radius, you're going to be using the snowman analogy. So as you can see, I have my little snowman here. If we were to put the snowman upright, so we don't need to have anything upside down. We don't want an upside down snowman. Those aren't fun. But you can see that with the head on top, the middle, and the bottom, it goes from small, medium, large. And so that's another way that you can remember the bigger corner. And then the way to see it sideways is we're going to take that same snowman, we're going to tilt it to the right. Okay, and we're going to see tomorrow that we're going to use this analogy with a snow cone, and you'll kind of get the same idea. But this is the way to remember radius. So small, medium, large going down to give you ultimately your bigger corner down here. Okay, so big corner in this side of the periodic table and your small corner up here. Hopefully that helps.